For today's video, we're going to be talking about complex numbers. You're going to have a section at the top of your notes called Number Systems We Know, about 5 lines in the middle called the basics, and the rest of your notes will be called Operations with I. So you guys already know some number systems, so the first thing we're going to do is write number systems we know. The first is labeled with this symbol. It's kind of like a fancy I. It's called the set of integers. So examples of integers might be like 1, -7, 0, 3, -2. These are all whole numbers, both positive and negative. And this symbol, I, represents all of those integers. So that's a specific set of numbers. Another set of numbers you know and love is the set of real numbers. Those are all numbers, like 1, like 5/2, like 2.7, or -2.7, like pi. It includes any number you can think of, any real number that is. The last set that we're going to learn about today is called complex numbers, and it's with this fancy C. Complex numbers consist of all expressions in the form a plus bi with the following 3 properties. So let's talk about what those properties are, and then we'll talk about why complex numbers exist. So the first property is that a and b are real numbers. A and b have to be real numbers. I represents the square root of -1. And if you think about it, I squared is equal to -1. But we'll talk more about that in a little bit. Last but not least, you can use addition and multiplication. You can use addition and multiplication as if a plus bi were a polynomial. Now some examples might look like this. Now think about what this means. A and b need to be real numbers, so any numbers. So I'm going to choose 5 minus 2i. That means that my 5 is my a, my 2 is my b, and my I represents the square root of -1. Another example might be 17 plus 5i, and again here my 17 is my a value and my 5 is my b value. Now what's the purpose of this? What's the why? Well, let's think about for a second all those times, and you don't have to draw this, but think about all those times that you had x equals the square root of 25. When you were given a question like that, you would say, oh, the answer is x equals 5. But what if you were given a problem where x equals the square root of -25? Do you remember what you would write? You used to write x has no solution. X has no solution. The introduction of complex numbers allows us to look at things like this, solutions like this, and imagine what would happen if this did exist, if the square root of -25 was in fact a real number. And if it was a real number, what would that mean to each function and things like that? So we're going to take a look at this. We're going to take a look at complex numbers and how they work together, and then later on we'll see how this affects their graphs and different functions. Okay, so let's start with the basics. The first thing I want you to do is copy down example 1 and example 2, pause the video, and then unpause it when you're ready to go through these 2 examples. Okay, so for our first question, they're asking us what is the square root of -2 times the square root of -9 times the square root of -3. Now because I know properties of radicals, I know I can put all of these under the same square root. that means that this is really asking me what is negative 2 times negative 9 times negative 3. So I'm going to multiply those together. I have a negative times a negative times a negative. So I know my result will be negative. And 2 times 9 is 18 times 3 was 54. Now I'm going to take my 54 and find any pairs that are hiding in there. That's a 9 times 6, 3 times 3, and 3 times 2. That means I've got 4 values in there. Now pay close attention to what I'm going to do here. I'm going to say this is 9 times 3 times 3 times 3 times 2. Now hopefully you agree that if I multiplied 3 times 3 times 3 times 2, I get 54. And if I multiply by negative 1, I get negative 54. Now remember, the square root of 1, square root of negative 1, is the same as I. So now when I pull out my pairs, I'm also going to circle my negative 1, because that means that the square root of negative 1 can be rewritten as I. So what comes out? For every pair, 1 comes out. So my 3, my I, it's my I, and what's left on the inside? 3 times 2, or 6. And this would be my simplified answer. Okay, let's try this one more time. For example 2, first I'm going to simplify what's under the square root. I have 4, because that's 2 squared, minus 4 times 1 times 4 is 16. If I subtract, I get the square root of negative 12. So now I'm going to take my 12, just like I did with my 54, and I'm going to break it into its factors. So that's 4 times 3, or 2 times 2 times 3. So the square root of negative 12 is negative 1 times 2 times 2 times 3. I'm going to circle my pairs and my square root of negative 1, because I'm going to replace that with I. For every pair, 1 comes out, so I get 2I, that's where my I came from, the square root of 3. And this would be my simplified answer. For our last step, we're going to look at see how does I work with operations. So when I add terms that have I, subtract them or multiply them, what happens? And I want to remind you that in the first slide we were saying that complex numbers act like polynomials. So this should feel very comfortable to you. I want you to imagine that these i's are like x's. So 3 plus 2x plus 2 minus 5i. For both a and b, I want you to think that we are combining like terms. So for both of these problems, we're going to be combining like terms essentially. Okay, my first question says this is 3 plus 2i plus, and I want you to notice that this is really a 1 that's distributing in here, a positive 1. And when that positive 1 distributes in, it's going to make this 2 be really 1 times 2, which is 2. And then this is really 1 times negative 5i, which is negative 5i. Now, multiplying by positive 1 doesn't change anything, but please keep that in mind for when we get to this problem over here. Now, from this point, back at question A, now we're going to combine like terms. So my like terms are these whole numbers, and then these complex terms right here. 3 plus 2 is 5, and 2i minus 5i is negative 3i. This is as simplified as that expression can get, and that's probably about as easy as it can get too. Okay, let's take what we learned from example A and try it in example B. So I have 3 plus 2i, and this time I have a negative 1 that's going to distribute through. Now take a look at what that's going to do to this last expression. This will be negative 1 times positive 2, making this a minus 2. And this will be a negative 1 times a negative 5i, making it a positive 5i. Now my like terms are still in the same place. I have 2 whole numbers and 2 imaginary numbers, 2 complex numbers. But when I combine them, they'll be a little different because my values are different. So I have 3 minus 2 is 1. and I have 2i plus 5i is a positive 7i. Okay, so that would be what adding and subtracting would look like. Our last task is to ask what would it look like if we were to multiply two terms that had I in them. Now the first thing I hope you notice is that this isn't a simple distribution problem. This 3 will have to distribute here and here, and this 2i will distribute here and here. Words that might be coming to your mind might be FOIL, you might be thinking factoring. All of those are good things to be thinking about. They're all within this, around this concept. So let's go ahead and do our distribution, keeping in mind that we're going to have 1, 2, 3, 4 products. Okay, let's start with our first one. 3 times 2 will give me 6. 3 times 5i will give me 15i, but it's a negative 5i, so it will be a negative 15i. Okay, still with me? So we just completed these two distributions. Next, I'll have 2i times 2. That's a positive 4i. And then I have 2i times negative 5i. That would be negative 10i squared. But I really hope you wrote down I squared here. Okay, now you're probably noticing that you have some like terms here. So that would be 6 minus 11i minus 10i squared. And you probably think you're finished, but you're not. There's a little bit more. I want you to remember that I is the square root of negative 1, and I told you that I squared equals negative 1, and I'd show you why. Well, I can prove it to you right now. I squared would be the square root of negative 1 times the square root of negative 1. That's a negative 1 times a negative 1, or, remember, for every pair, 1 comes out. So here's my proof that I squared equals negative 1. That means whenever I see an I squared, I can replace it with a negative 1 to further simplify the expression. So here, when I have 6 minus 11i minus 10i squared, it really is 10 times negative 1. So let's simplify this. We get 6 minus 11i plus 10. My final answer would be 16 minus 11i. If I asked you where was the A and the B, could you tell me? I hope so. This is my final answer.